NMR and IR data presentation by Claire Hans. Looking at the given IR spectrum, it is evident that the molecule contains a CH bond because there's a medium intensity sharp frequency at around 3000 centimeters inverse. At around 1500 centimeters inverse, there's a medium intensity frequency with two bands, indicating that a C double bonded C is present in a ring structure. Also, at around 1200 centimeters inverse, there's a strong intensity frequency which relates to a CO bond. Beyond the 1200 centimeters inverse mark, known as the fingerprint region, the frequencies become difficult to distinguish and therefore are not accounted for. After using the given IR and NMR data, it was determined that the molecule has a molecular structure of C10H12O, corresponding to the molecule anethol. On the NMR, signal A at 7.56 parts per million has an integration value of 1.54, assumed to be two hydrogens. The signal is split twice because it is adjacent to one hydrogen on the adjacent carbon. Signal B at 7.11 parts per million with an integration value of 1.48, assumed to be two hydrogens, is also split twice by the adjacent hydrogen. Both of these CH2 signals correspond to the hydrogens within the ring structure of the molecule. The hydrogens that are 2 bond lengths away from the oxygen will show up as one signal and at a higher ppm value than the other grouped hydrogens, which are 3 bond lengths away from the oxygen. Signal F at 6.83 parts per million has an integration value of 0.1. This integration value should be 1, as this represents a single CH on the molecule. This signal should be representative of one hydrogen that experiences splitting twice because of the one adjacent hydrogen. Possible errors for this NMR data could include that the leftmost peak on signal C should actually be the second split for signal F. It is possible that this peak was absorbed and shifted over onto signal C. Signal C at 6.49 parts per million has an integration value of 1.30, assumed to be one hydrogen. This signal is split 6 times by the adjacent hydrogens on signal F and signal E. Signal D at 4.07 parts per million has an integration value of 3, representative of a CH3 present within the molecule. This signal is adjacent to an oxygen and not adjacent to any hydrogens, so therefore only exhibits one peak value. Signal E at 2.15 parts per million has an integration value of 2.71, rounding to 3, representative of another CH3 present within the molecule. This CH3 is adjacent to one hydrogen and therefore will split 2 times. The reference peak chosen was chloroform D at 1.56 parts per million. There is a signal adjacent to this reference peak, however, it can be assumed that this peak is not representative of another hydrogen within the molecule. Most likely this peak is due to a contaminant.